Good morning, everybody. This is the second day of the D-Day of the PhD school in ICT. This is the day of the students that are at the 22 cycle and the 23 cycle. And I'm not sure that in so few minutes you will be able to show us all the work you are doing and you are carrying on, but it's enough to give a spot of your activity. So the presentation of today is about 5 students in computer engineering and science course and 2 students in electronic and telecommunication one. And the first one is Giovanni Gualdi, then Nana, Puviani, Sala, and Villani, Grossi, and Sergi. Okay, the first one is Giovanni Gualdi.
Thank you very much. Thank you. Okay, so I will talk to you about my research activity in 2008 by the name Object Tracking with Freely Moving Camera. And just to give you a short introduction, so my research founds come from the PRIN called FreeSurf, that is about people surveillance from mobile cameras. And in 2007, so the first year of my PhD, I focused on studying video streaming, optimized video streaming for mobile surveillance. And in 2008, I worked more on computer vision algorithms to work on mobile video surveillance. So we will talk about this. And so I tackled a very generic object tracking, not focused on people only. And you can see a few conditions that we want to deal with. So moving camera, freely moving camera, uncalibrated view, clutter background, scene cuts, so pretty generic, differently from what we handled up to now in our tracking applications in our lab. So we decided to use a basic feature detection on the bottom and then on top of it graph theory to impose the tracking. So let's see the 2 parts. The first part is related to the feature detections. So imagine that we build up a model of the object that we want to track that is made of several parts. For example, here we have 3 parts. And we imagine here to use color features, but it's not necessary to use those. And so we extract a model. And then what we do, and each part has a different semantic meaning. There is the cable here, okay. For example, head, face, for example, neck and torso. And for each new frame that we have, we project the frame through a part of the model, and we obtain a probabilistic map of that part. For example, the probabilistic map of the presence of the face in the image, of the presence of the neck, of the presence of the torso. And then, on each of these, we scatter particles with a distribution that can be uniform or Gaussian distributed, depending on the tracking in the previous time instant. And then for each of these particles, we grow them in order to encompass the bigger probabilistic blob, let's say. So we basically extract many clusters. And of course, there are many redundant clusters, and we are not scared about redundancy and wrong false positives, but what we care is that among those, there is the true one. There must be the true one. And for each of these clusters, we extract attributes like center of mass, weight, density, and other stuff that we will use later on. So this is all about the feature detection. And on top of them, we lay this layer based on association graph and dominant set that I will talk to you right now. So basically we have a model graph that represents the object that we want to track. The model graph has several nodes. Each node has a different semantical meaning, a part of the object, like head, neck, hands, right and left, for example. And there are links between the parts. It's not a complete graph, and the looser the graph it is, the more flexible it is. The more complete it is, the less flexible, of course. So this is the model that we would like to track in the time. And then for each frame, we have a labeled graph that is made of cluster, and these are the clusters that we saw before. But each cluster belongs to a specific part because it was created through the model, through a part of the model. So we know that this cluster should be a head. This cluster, one of them should be the neck among the necks, and so on. And then we build on top of it a complete p-partite graph that is blind. I mean, just a complete p-partite graph. And so the tracking would be to find the best subgraph isomorphism from here to here. So best in the meaning of maximum coherency. And if we could extract the best isomorphism, that would be our tracked object. So how do we do this? We basically construct another graph that is called association graph, that is a product of these two ones. And I won't go in detail for brevity, but each node is made of pair of edges. So, for example, this node is made of AB and 1, 2. So basically pair of consistent edges. Head with head, neck with neck. And then we have links, valid connections, and then on each link we give a coherence measure. And here we use the attributes that we extracted during the feature detection part, like mass, density, position. And this basically gives the coherency measure between this edge and this edge. At this point, there is a theorem that comes to help us and says that the maximal weight subgraph isomorphism between the graph, the model graph, and the label graph is exactly the same as finding the edge weight clique in this association graph. And this is a good theorem for us because there is a framework called dominant set that gives us an heuristic to find not very easily, but in a pretty short time, pretty short time, not real time, but not even ages, to find this. That is basically the extension of a clique on an unweighted graph to a weighted one. And so, through the dominant set, we extract the maximum weight clique, that might be this, for example, and we back project it to our actual nodes, and the nodes that are touched by the dominant set is the tracked object. So why using dominant set and not just a click search, a flat click search? Because we get for free through the coherency measure the exclusion of nodes that are not coherent with the others. For example, with just click search, a false positive of the head would be inserted anyway, forced to be inserted. But with dominant set, we get for free also the exclusion of nodes that have low coherency with respect to the others. So that is pretty a good property for us. And now I want to show you a couple of results. There is a video. This is the legenda, the time sequence of the video, where we have movement, zooming in, zooming out, rotation, sync cuts at the end. And we want to track 5 parts, like head, torso, hands, and pants. And when you see red ellipses, don't get confused by the color space, because it's just a transformation for my work. But the key point is, notice the ellipses around the parts, and they will be always red. That means correct tracking, except a few times that the hand, for example, disappears because it gets confused with a fence. Let's see. So of course it is slowed down for ease of. So you see this hand that gets confused, so it becomes green. It means that it is not coherent when it is the hand here. And then here you will see that the head disappears because it gets cut down by the movie, and the algorithm suspend the tracking of the head but when the head appears again, it goes up again. And then there are a few scene cuts at the end. And then another one. This is different with, there is no background suppression here. And we do, basically, we try to recover after a total occlusion. And you see when there is the total occlusion, the algorithms say not reliable energy. Everything becomes yellow, means that the tracking is suspended. But when the guy appears again, the tracking is recovered. And you see that we are using color here, and you see that the color of the black is not really informative to us because everything in the background, I mean, most of the things in the background are black. So it's pretty good. A few results, but I cannot talk about them. So just a glimpse. For 2009, we will apply these things, the research of 2008, 2007, and also what I will do in 2009 for safety in construction working sites. And we will start trying to understand where the workers are and if they wear the helmet. And I'm close to the end. These are my publication in 2008 only. And there's a journal that was more about the work in 2007, and then a few other works, one that was selected to go in a state-of-the-art survey. And I think this is all, so if you have questions.